just moving this to make sure you can see within those borders. Over here, just put another little line. It's amazing what you can use a clamp stand for. Okay. All right. Next mechanism we're going to talk about is SN1. And this time, this is the nucleophilic substitution reaction for tertiary haloalkanes. So let's go for X again as my halogen. Okay, I'm going to show CH3, CH3, CH3. So you can see that this is the tertiary haloalkane because the halogen is bonded to the carbon, which is bonded to 3 other carbons. Okay, so this time the mechanism is slightly different. You might think that the nucleophile can attack it again, just like before. Well, no, it can't do that this time because these groups are bulky groups. Okay, they're going to get in the way and prevent this nucleophile from attacking that carbon. Okay, so I'm going to remove all of that. I'm going to talk about what actually happens instead. Okay, so the first step of this mechanism might seem a little bit strange because what actually happens is that this bond just breaks. Okay, that is why it is quite a slow step of this reaction because you're simply waiting for that bond to break. Now the reason why it would break is because it's in suitable conditions, the product that you form is favourable, so you are gaining energy back from the energy that you've lost in breaking this bond. So it's all about energetics and thermodynamics. So the key thing here is that we are breaking the bond with the halogen. Okay, what that then forms is an intermediate. This intermediate this time can be isolated, it can be stopped here, and it is reactive. Okay, and the reason why this intermediate is reactive is because it has a positive charge. Okay, you can see it must have a positive charge because it's lost the electrons from this bond, that's now broken, to leave us with this. And we call this a carbocation reactive intermediate. Oh, Matt just got off the screen there. Okay, not forgetting as well to put our halogen that we have lost here. Okay, what can happen now is your nucleophile, so let's stick with the hydroxide, can attack at either side. It can either come in this way or it can attack this way. Okay, notice how both of my arrows I've tried to show coming from this lone pair of electrons because that is what an arrow shows us, the movement of electrons. So I would be incorrect to draw my arrow from here. Okay. What this then means is that I have two possible products that can form. One with the hydroxide on the left and one with the hydroxide on the right. Okay, so I'm going to rub this out, get a little bit more space and draw the next step. Okay. In fact, to save a little bit of time, I'm just going to go backwards here and draw what the products would be. So, if we had the orange pathway, then what you would have is this product, whereas if you had the blue reaction occurring, you would have this product here. Okay, so in this example, it actually doesn't matter, because actually what we've ended up with is the same product anyway. Okay, so you wouldn't get a mixture. When you would get a mixture is if these groups were different. Okay, so if these groups were different, so let's change them into just X, Y, and Z, meaning that this one now is X, Y, and Z. You can now see that it matters if the groups are different, because what you have now formed is optical isomers, which, remember, an optical isomer is any molecule that has a carbon with 4 different groups attached. Okay, so do look out for that. They love to ask questions where it starts off with a nucleophilic substitution reaction, and then it goes into talking about isomers, optical activity, and so on. Okay, this step here, because we have a reactive intermediate with a positive charge reacting with something that has a lone pair of electrons and negative charge, this is going to be fast. So that's going to happen super speedy. So the slowest part of this reaction is the first part, where you're waiting for that halogen to drop off there. Okay, a couple of things that we can say about this. We could say a little bit more detail about this carbocation. I could say it was a tertiary carbocation because the carbon is bonded to 1, 2, 3 different carbons. I could talk about the shape, so I could say this was a trigonal planar shape, in case you asked for that. What else do we need to talk about? Oh, and this time we would say it was a non-stereo specific attack, because the nucleophile can go either side. It's not limited to just attacking from one side. It can come either side of the molecule. Okay, I'm going to whip that out, and we're going to do one more video to talk about where the numbers from SN1 and SN2 come from.